All right, welcome to the Week 7 Math 2419 review. This review session will be covering, we'll just start getting into functions of several variables, and then we'll talk about some partial derivatives and intro to differentials, multivariable functions. So, first off, we can start by talking about what is a function of several variables. Well, a function of several variables, simply put, takes multiple functions as input. And one example of this would be the volume function for volume of a cylinder. You remember the volume of a cylinder is pi times the radius squared times height. And in this case, we have two independent variables, the radius here and the height here as well. Because the volume, we can write the volume as a function of both radius and height together, being equal to pi times radius squared times h. And we can change either height or radius to change the volume, and the radius and height don't necessarily have to relate to one another. So when we have one fixed value of a radius, we can change the height as much as we want. When we have one fixed value of height, we can change the radius as much as we want, and vice versa, so on. And one thing you can kind of think about this as is you recently covered vector-valued functions, and vector-valued functions take one variable as input and give multiple things as output. Vector functions of several variables are kind of the opposite. They take multiple things as input and give one thing as output. In the future, you might start seeing things that take multiple variables as an input and give multiple things as output, but we're not going to discuss that today. All right, so let's start talking about some domains of functions of several variables. We'll start off with an example. Find the domain of the function tangent of x plus y. Okay, well, first we need to think about where could this function possibly give us some value, or where in this function would we need to perform something that's just not allowed. And one thing we know we can't do is we can't take the tangent of pi over 2, because that tangent is sine over cosine, and cosine is 0 when your angle is pi over 2, and we can't divide by 0. So we know that we can't have pi over 2, or really any multiple of pi over 2. We can't have pi over 2 plus any k pi, where k is an integer. Well, in order to find the domain, we simply say x plus y, this inside portion of our tangent, is not allowed to be equal to pi over 2 plus k pi, but everything else would be allowed. In fact, if we wanted to sketch the domain of this, well, it's going to be actually a whole plane, basically. Not quite a whole plane, but we're going to have a series of, well, not necessarily a series. Let me clarify. We'll just sketch it. Anything that would not fall on any of these lines, x plus y equals to pi over 2 plus some integer multiple of pi, would be allowed. So if you think about this, we've got, here is one line corresponding to x plus y equals to pi over 2. Oops, I sketched that the wrong way. That should be this way, like that. There we go. And this corresponds to the line x plus y equals to pi over 2. And of course, we could sketch another line that would be pi above it. And this corresponds to x plus y equals to pi plus pi over 2. And we could continue sketching these lines like so. And we know that anything on these lines is not allowed in our domain. But anything not on these lines would be allowed. So really anything in any of these areas just not on the lines is allowed. So our domain is actually the whole plane without these lines in it. Let's do another example to maybe clarify things. This one, we're going to say sketch the domain of the function f of x, y equals to the square root of x squared plus y squared minus 4 divided by x plus y. Okay, well, first we need to identify our problem points where we could end up with a number that maybe isn't allowed within the boundaries of math. So one thing we know we can't do, we can't divide by 0. So that tells us that x plus y is not equal to 0. Another thing we're not allowed to do, we can't take the square root of a negative number. So we need to make sure that x squared plus y squared minus 4 is always bigger than 0, or x squared plus y squared is always bigger than or equal to 4. So we simply need to sketch the plane that follows both of these rules. 1, x squared plus y squared is bigger than or equal to 4, and 2, x plus y is not equal to 0. So the line x plus y is not equal to 0 looks something like this. Everything except for anything on this dotted line is okay. And of course, this x squared plus y squared equals to 4 would be a circle of radius 2 like so. Here, my circle drawing skills are wanting. Let's see if we can get a decent one. Good enough. And we know that it has to be that our value x squared plus y squared has to be bigger than or equal to 4. So anything outside this circle is okay. Anything outside the circle and not on this dotted line would be okay for our domain. Make sense? In that case, I'm going to go ahead and give you a quick practice problem. Go ahead and try to write a function with the domain shown in this picture that I'm going to draw. And the domain is going to look something like a circle of radius 1, and anything inside this circle is allowed, but not anything on the boundary. Go ahead and try and write a function with that, and I'll give you a minute or two to work on that. All right, how's it coming? X squared plus y squared is equal to 1. Okay, that is a function of two variables. However, if we sketch x squared plus y squared is equal to 1, the domain of that would actually just be the domain would actually end up being a circle that looks kind of like this. It would be a circle of radius 1, not filled at all. The reason being is, well, in order to have a radius of 1, in order for x squared plus y squared to equal 1, you'd have to have the x component and the y component equal to this radius. So that's a good guess, but not quite. Let's go ahead and go over the answer. So if we were to write this picture out in a bit more mathematical terms, we could say, rather than x squared plus y squared is equal to 1, we would say it has to be smaller than 1. So, because that would encompass everything inside this circle, but not necessarily on the boundary. Make sense so far? Cool. So, if we wanted to figure out a function that has x squared plus y squared smaller than 1, not smaller than or equal to, excuse me. A good way to do that is to use a square root, because square roots by their nature have to take a value that's bigger than or equal to 0. So that's good for getting inequalities. So in order to write a square root that would be bigger than or equal to 1, we could write it something like this. 1 minus x squared minus y squared. And basically all I did here is I took this inequality here, and I said, okay, I'm just going to subtract x squared plus y squared from each side. So 0 is smaller than 1 minus x squared minus y squared. And that gives me this inequality. I can then put this straight under my square root. Of course, that would actually introduce an equal to, and in order to get it to not be equal to 0 exactly, in order to essentially take out this 0 point, what we can do is essentially just divide by that, because we're not allowed to divide by 0. Does that make sense? It's a bit weird. Let me see if I can explain it in a different way. So why don't we keep this original form? Like, why don't we keep this 1 minus x squared minus y squared right here? Is that what you're asking? Okay, so good question. The reason being is if we took just 1 minus x squared minus y squared, well, we know that whatever's on the inside has to be bigger than 0, or bigger than or equal to 0, excuse me. It has to be non-negative. But what we're interested in is specifically where x squared plus y squared is less than 1, not less than or equal to. We have this dotted boundary, which means we're not allowed to take things on this boundary. If we rewrote this inequality right here, that would give us 1 is bigger than or equal to x squared plus y squared. In order to get rid of this or equal to portion, we need to make sure that we're basically trying to introduce division here to say this bottom term cannot be equal to 0, because that's where our equality comes in. Basically, we're changing this portion into this portion to change this into a dotted line rather than a solid line. We're eliminating this boundary circle from our domain. Does that make sense? Yeah. So that's kind of the whole point of the division. Yeah. You probably won't see a ton of problems like this, or really any. I just think that they're sometimes helpful to start visualizing domains of multivariable functions, because the domains can look like a bit weird at first or feel a bit weird to work with. So sometimes seeing domains sketched out as pictures can help. All right, but let's move on from domains. We're going to briefly touch on function composition, which is pretty interesting. If you remember from, I guess, way back in algebra, if you have two functions f of x and g of x, well, you can take the function composition f of g, which would be f of g of x like this. And that's how you do things for single variable functions. One thing though, you might not be able to do that with multivariable functions. So if we say like f of xy and g of xy, well, you can't really say f of g of xy because g takes in two variables as input. So does f. But g only puts out one variable as input. So if we have two variables, x and y, as input, like so, well then g of xy turns it into one thing. But f, in order to work, needs two things. And we can't necessarily know what that second item would be, so we can't necessarily take a function composition of two multivariable functions. You can compose multivariable functions with single variable functions. So for example, if you have your same f of xy and you have a function h of x that takes in one variable, well, you could do h of f of x. And that would be, or not h of f of x, h of f of xy, because h only takes in one thing as input, f gives out one thing as output. So you would take in two variables, x and y, perform your f operation on them, get one variable as output. Then you would take that one output and use it as the one input for f. You can also, you might see this in more advanced courses if you're taking them. You could potentially even see vector valued functions composed with multivariable functions. So if f takes in two variables as input, and you have a vector valued function r of t that gives two variables as output, call that a of t and b of t, well, you could take f of r of t, because you take your one input t, put it into r gives out two variables as output, you use those two variables as the two inputs for f. So basically you just have to make sure that when you're doing function compositions, your output of your inner function matches the input required by your outer function. So if they don't match, you can't do a function composition with them. I don't have any practice problems or example problems with these because it's just a brief note that I wanted to touch on briefly. So if you have any questions, go ahead and ask them. But if not, I'm going to go ahead and move on to the next topic, which is level curves. Okie day. Level curves are pretty important. They are one way to help visualize functions of multiple variables. Let's jot that down. So usually we have functions of multiple variables, and they take the form z, which is our third dimension, basically, is some function of x and y. And this creates a 3D graph. But sometimes these can be pretty hard to visualize because it's just a lot to take in. So what we do with level curves is we say, well, instead of looking at all the values of f of x, y, we're just going to look at it where they're equal to one constant. So we're looking at one flat level of our function. Think about if you had a 3D graph, let's say it looked something like, I don't know, something like this. A level curve would be if you took a plane that's horizontal and just chopped straight through it, like that. And then you looked at just the cross section you made. That's kind of what a level curve is. If you've seen a contour map, like in geography, those are often what maps of level curves look like. So let's go ahead and do an example. Let's consider the level curves of this function z is equal to x squared plus y squared. Well, if we looked at the function z is equal to x squared plus y squared, I can go ahead and actually tell you what this looks like. It's what's called a paraboloid. So it looks kind of bowl-shaped, but in 3 dimensions. So it's got like almost a shape kind of like this. But if we wanted to take level curves, what we could do is we just set z, this third dependent variable, equal to various constants. So if we let z is equal to 1, well then that tells us that x squared plus y squared is equal to 1. That's a circle of radius 1. If we let z equal to 2, well then x squared plus y squared is equal to 2, and that's a circle with radius square root of 2. If we let z equal to 4, and so on, we get x squared plus y squared equals to 4, a circle of radius 2, etc. And if we plotted all of these out just on one flat 2D plane, well, here would be our circle for z is equal to 1. Here z is equal to 2. Here z is equal to 3. And if you pay really close attention, you would actually notice that the circles get closer and closer to each other, which tells you that your function is getting steeper and steeper. And this plot of various level curves is called a contour map. And frequently you would want to label them with the heights. So this would be 1, 2, 4, etc. And one last note, if we let z equal to 0, well then x squared plus y squared is equal to 0. And this is, of course, only satisfied by the point 0, 0. So our 0 level curve would just be the one point centered at the origin. All right, so that is the idea behind a contour map. Why don't you go ahead and try one out for yourself? Go ahead and try and sketch the contour map for this function f of xy equals to x squared plus y. I'll give you a couple of minutes to work on that. See, your graph is like a set of downward parabolas for every time you plug in a value of c. Yep, that is exactly right. It is what it is supposed to look like. See, if we wanted to work through the level curves, you could set z equal to 0 and see y is equal to minus x squared. I simply moved my x squared over to the other side to get it in terms of y. If you let z equal to 1, well, that would tell us 1 is equal to x squared plus y, so y is equal to 1 minus x squared. If we kept doing this, z is equal to 2, we get y equals 2 minus x squared, and so on. If we plotted those to make our contour map, well, it would just look, like you said, like a series of downwards parabolas. There's one, there would be another, and they would all be basically evenly spaced. They're not in my picture because I'm not very good at drawing pictures. And if we labeled The heights, this would be like a -1, a 0, a 1, and a 2. So these ones would be higher than the others. Do you need to know how to graph in 3D coordinates? That is a good question. You should ideally know the shape of like some basic things. Professors don't really tend to expect you to know the shape of like more complicated things. And they don't really expect you to be able to draw them very well, just because sketching things in 3 dimensions is hard. Contour maps do tend to help. Um, let's see if I can pull up a 3D graph for this one really quick. Just a moment. Oh, my computer's being uncooperative. Won't be able to pull up a graph right now, but contour maps can help because this would tell you like your z value is -1. So you could say this parabola right here, this -1 should be considerably lower than this 2, 1 way up here. And if we wanted to sketch that, well, we could kind of see that it would make like a bowl shape, but like a half bowl that's kind of open, and it gets wider. So I can try and sketch this. We'll see how well it goes. It would look kind of something like maybe this, where these portions are open on one side and it slopes downwards towards the middle, like that-ish. There we go. I think we can pull up the graph now. And perfect. Let me just share that with you really quick. All right, and you can see this is what the graph would kind of look like. It's like a tilted parabola, almost a tilted stretch parabola, which is exactly what our level curves show. And if we put a horizontal plane in at any space, we would see that we would get a parabola. Does that kind of clarify things as far as how level curves can kind of show the shape of a 3D graph? But as far as like graphing a lot of things in 3D, I wouldn't put it too much focus on that, because most of the 3D shapes you'll end up being asked to even sketch out are pretty simple, like spheres, ellipses, which have really basic and obvious formulas. Yeah, yeah, I mean, I think it's mostly important if you can kind of describe it a bit with words. Um, then professors, it's just not something professors tend to ask about a lot because they end up with a lot of pictures that look like this, a lot of pictures that basically make no sense because no one's good enough at drawing in math. Um, so they tend to focus a bit more on can you perform the calculations with these multivariable functions. Does that answer your question? Yeah, cool. All right. They might ask you to sketch contour maps, though. That is something that they might ask you to do instead of sketching something in 3D because you should be able to sketch things in 2 dimensions. That is something that's a bit more expected. Let's see, another quick definition or thing to remember. Level curves don't necessarily have to be 2D. For instance, you could have a function that takes in 3 inputs, and that could be equal to some dependent variable. We'll call it W. If we wanted to put a complete graph of this, it would actually have to be in 4 dimensions because we would need 3 dimensions, 1 for each of our inputs, plus 1 dimension for our output. So obviously we can't sketch that because we can't sketch things in 4 dimensions. So what we can do is we can sketch what's called level surfaces. And that is a 3-dimensional level curve, where we replace this dependent variable with a constant. So for example, 1 is equal to x squared plus y squared plus z squared. This would be a level surface because we have 3 independent variables equal to 1 constant. And this is, of course, the unit ball. So it's just a sphere centered around the origin. And that is specifically in 3 dimensions, a level curve in 3D is known as a level surface. But you can have level curves in higher dimensions and stuff. So that is something that's just good to keep in the back of your mind occasionally. Let's do one last practice problem with contour maps. This one's going to be a bit harder. Sketch the contour map for, we'll say f of x, y equal to x square root y plus 4. And just a word of caution, make sure that you are paying close attention to the domains of your independent variables when you're taking your level curves. Good luck. I'll give you a few minutes. All right, how's it coming? Got a horizontal asymptote at y is equal to -4, straight vertical line, c is equal to 0. Then it starts spreading out a bit, uh, curves at -4. All right, kind of like a letter L. All right, I can see that. It looks like you're getting about half the picture. Did you consider any curves that might fall below 0? Because sometimes those are important to consider as well. Yes, all right, cool, cool. In that case, let's just go ahead and work through it. Seems like you got a pretty solid grip on it. Um, let's see, we'll just start coming up with some contour, some various level surfaces for level curves for just various z values here. When we let z equal to -2, well, that tells us that -2 is equal to x times the square root of y plus 4. If we rearrange, we get 4 over x squared minus 4 is equal to y. But in order for z to be -2, well, then either x or the square root of y plus 4 would have to be negative. Since the square root of y plus 4 would never be negative, that tells us x has to be smaller than 0 in order to get a negative z value. Also, y has to be bigger than or equal to -4, because if it's smaller than or -4, we would end up taking the square root of a negative number, so that's not allowed. Pretty similar situation for z equal to -1. We get 1 over x squared minus 4 is equal to y. Again, x has to be smaller than 0 and y bigger than or equal to -4. At z is equal to 0, well, that tells us, yes, either x is equal to 0 or y plus 4 is equal to 0. So we have essentially like an upside down t, where x equals 0 or y is equal to -4. At z is equal to 1, we could rearrange and get the equation 1 over x squared minus 4. But since z is positive, that tells us, since the square root of y plus 4 is always positive, we know that x also has to be positive to keep this z value positive. And of course, y is still bigger than or equal to -4. And we'll do one more. At z is equal to 2, get 4 over x squared minus 4. And again, x has to be positive, and y bigger than or equal to -4. Cool. And if we sketch all of these out, I'll just start with the 0 curve. Right there, we have the line either x is equal to 0, so we'll change that to a different color. Go with the green. Either x is equal to 0 right down the middle, or y is equal to -4 right there. That would be our level curve for 0. And we'll move on to the positives. When z is equal to +1, we get y equals to 1 over x squared minus 4 for only positive x values. So that would be something kind of like this. And for z is equal to 2, the same thing, but we have a 4 over x squared instead. Something kind of like this. Then for the negative values, we only want to consider the negative x's. And it would kind of just be like a negative symmetric version of something like this. And what that kind of tells us is we essentially have like a pattern where our function starts off really high over on this side and it slopes down this way. If we wanted to look at the actual graph of that, let me pull that up really quick. There we go. You could see that's exactly what we're being shown on our graph. We start off high for positive x values and then slope downwards. And we are seeing these almost level curve shapes. Of course, all our y values are bigger than -4. And we have these asymptotic curves at various heights. And of course, right at the value where our z value is equal to 0, we can see our x value is also equal to 0. And we also have this one line running straight across y is equal to -4 when z is equal to 0 as well. All right, that makes sense. All right. In that case, we'll go ahead and move on to something other than level curves. Let's talk about partial derivatives now. So partial derivatives, obviously when we have multivariable functions, if you wanted to try and take the derivative of them, well, how do you take the derivative with respect to two variables at once? The answer is you don't really. You take the derivative with respect to basically one variable at a time, and those are known as partial derivatives. So the way we do that is we basically take the derivative, we only consider one variable at a time, and we treat all the other variables as constants. So for example, if we have some function f of xy equal to 2x plus xy plus e to the y, well, we could take the derivative with respect to x. This is how we denote that, f with a little x written down into the side. This is known as the partial derivative with respect to x. And all we do is we take the derivative with respect to x and treat all the y's like constants. Derivative of 2x is of course 2. Derivative of xy, well, we treat y like a constant, so the derivative of x would be 1. Since our constant is attached, we multiply that. And since this term, e to the y, doesn't have an x term in it, treat it like a constant. Derivative of a constant is 0. So our partial with respect to x would just be 2 plus y. Next, we could consider the partial with respect to y. 2x doesn't have any y's in it, so it's all treated like a constant. Derivative of a constant is 0. Next, we look at the xy term. Derivative of y is 1. Treat x like a constant. X times 1 is x. Lastly, derivative of e to the y is e to the y. And the way we would interpret this is on a 3D graph. This would be like the slope in the x direction. So if you were to hold y constant and walk in the positive x direction, this would be the slope you would experience. And for the partial with respect to y, this is similarly the slope in the y direction. So if you were to simply start walking exactly in the positive y direction, that would be the slope you experience. That's kind of one interpretation of partial derivatives. So why don't you go ahead and try a couple out. Take the, yeah, we'll just say find partials. For f of xy equals to sine of xy plus x e to the y. find f sub x, f sub y, and yeah, I'll give you just a minute to do both of those. Just let me know when you're done. How's it coming? Let's see, for the x derivative, you got y cosine of xy plus x e to the y. You also have a plus e to the y in there. All right, and cool. All right, let's go ahead and double check that really quick. If we were to take the x derivative, well, derivative of sine of xy, we treat the y inside like a constant. Derivative of sine of u is cosine of u times the derivative of the inside. So we would have cosine of xy times the derivative of xy. Derivative of xy with respect to x, treat y like a constant. Derivative of x times y then would just be y. Next, derivative of x e to the y. The e to the y does not have, we can just treat that like a constant. So derivative of x times e to the y would be 1 times e to the y. We don't actually want to use the product rule here because there's only one term in here with an x. So our x derivative would just be cosine of xy times y plus e to the y. So you're close, but not quite. Did you come up with a y derivative? course. We got f sub y is equal to x cosine of xy plus, again, really close. You made one slight mistake. You are correct. The derivative of sine of xy with respect to y would be x cosine of xy. I think your mistake, though, is you took the derivative of e to the y and got 1. But remember, the derivative of e to the y with respect to y would just be e to the y. We leave our x out front as a coefficient. Make sense? Yeah. So we're taking the derivative with respect to y. So one way to think about it is like if we were taking the derivative of 2e to the y with respect to y, well, we just leave the 2 out front because it's a constant coefficient. The derivative of e to the y would be e to the y. Same situation we have right here, except instead of having a 2 right here, we have our x variable. But since we're treating it like a constant, it just stays out front like that. Um, yeah, of course. So those would be our first partial derivatives. But then we can actually find second partial derivatives. For example, the second derivative with respect to x twice, and that would be the derivative with respect to x of this first derivative with respect to x. So we take this function here and take the derivative with respect to x. If we did that, well, we would take the derivative of y cosine of xy with respect to x. The y is just a coefficient out front, so we can basically put it down, ignore it, take the derivative of cosine of xy. The derivative of cosine of xy with respect to x, well, that would give us negative sine of xy times the derivative of the inside. Derivative of xy with respect to x, well, we take the derivative of x, we get 1, treat y like a constant, just like that, then plus whatever the derivative of e to the y is. But the derivative of e to the y with respect to x is 0. And if we rewrote and simplified, that gives us minus y squared sine of xy. Now go ahead and try finding the other 3 second partials. Yeah, and I'll give you a couple minutes to do that. Did you get any answers yet? You got for f sub yx, you got cosine of xy minus xy sine of xy plus e to the y. Exactly right. Nice work. All right. F sub xy, put cosine of xy minus xy sine of xy, but then that last term I think should also be plus e to the y. Maybe a double check. I don't think it should be plus 1. Yep. Then for f sub yy, see for the derivative of f sub y with respect to y. First we take the derivative of x cosine xy. The x up front is a coefficient. We leave it there. Derivative of cosine of xy with respect to y would give us multiplied by the derivative of the inside. Overall, we get negative x squared sine xy, right? And then plus, I believe that's an x e to the y again. Because we take the derivative of e to the y with respect to y, we get e to the y, leave the x out front as a coefficient. All right. So these would be our 4 second partial derivatives. Of course, you could keep going. If you wanted to keep going, you could find partial with respect to x 3 times, with respect to x twice, with respect to only once, and then your partial with respect to y all 3 times. This is where I want to bring up something else. The other partials you might think are there would be, well, what if we did with respect to x twice, but we did with respect to y first? Or x, y, x. The cool thing about this is these derivatives are all actually the same as long as they have the same number of x's and y's in the bottom. So for example, f sub xyy is the exact same as f sub yxy which is the exact same as f sub y, y, x. You actually saw this in this previous problem because we got f sub xy is the same as f sub yx. Yes, this is a theorem. It's known as Claro's theorem. And basically it says your partial derivatives are going to be the same as long as they have the partial derivative with respect to the same variables. So it doesn't matter if you do the derivative with respect to x and then y, or the derivative with respect to y and then x. It just matters that overall variables in the variables in here are all the same letters. It doesn't matter what order they're in. So if you had some function and you took the derivative with respect to x 10 times and then y twice, well, that would be the same as saying taking the derivative with respect to y, then x 4 times, then y again, and then x 6 times. Because here you have x 10 times and y twice, and here you still have x 10 times and y twice. So you would say these two partial derivatives would be exactly the same. And that can be helpful because it means you're not computing quite as many partial derivatives. You good on that little theorem right there? Cool. In that case, I don't think I'm going to get into differentials today because that would require quite a bit of time and we're just about out. So I'm going to go ahead and say thanks for coming. That's all for today. We'll talk about differentials next week, which is good because I think we're just barely starting them in class. So thanks for coming and have a good week. Of course, if you got any other questions, you can ask them now, of course.